right, everyone. It is my pleasure to announce our next speaker. Let's see, forgive me if I mispronounce your name, but Nursultan Kuanyshov?
Yes.
Close.
Yeah,
okay,
you are
perfect. Wonderful. Who will be telling us about this LS category of group homomorphisms. Thank you.
Thank you, Molly. First of all, I would like to thank the organizers who organized this wonderful workshop. And so title is the Lusternik-Schnirelmann category of group homomorphism. And in this talk, basically the first part will be motivation why we study a Lusternik-Schnirelmann category. And then like we formulate the questions and so we will give some results. And this is a joint work with my advisor, Alexander Tranishnikov, at University of Florida. So let's start from the definition. So what is the LS category or Lusternik-Schnirelmann category? So Lusternik-Schnirelmann category of topological space is that minimal number case such that X is covered by K+1 open sets, and each open sets are contractible in the ambient space, or namely in the X. And this is the important invariant. Namely, it has the homotopy. For example, if so, oops, sorry, I'm trying to write it, but so if X is a homotopy to the Y, then the LS category of X is we get the LS category of Y. And this is a important invariant because it gives us the number of the critical points for the smooth real valued function. And well, here's critical points is studied the Morse function, but in the Lusternik-Schnirelmann category, we don't need our function to be a Morse function. So you can apply for any smooth value, smooth function. And now, so as you can see that here, I want to do the remark. So if the space is, oops, let me, yeah, I'm having a technical issue. So if, hold on. So yeah, so if the space is A and R, absolute neighborhood track, then we can replace our open set with the closed sets. And now we can define we can generalize this LS category for the map. So LS category of map is a minimal number case such that X is covered by K plus open sets. And when we restrict our function to the each open set, it has to be null homotopic. And from this definition that we can see that if F is the identity map, then we get our LS category of space. And now LS category, how we define the LS category of group homomorphism. So we define it as a LS category of group phi equals to just cut of B phi, where a B phi is a map between their classifying spaces, namely the B gamma and the B pi. And it's known in algebraic topology, these spaces are Eilenberg-MacLane spaces, and spaces that have a contractible universal cover, or in other words, all the higher homotopy groups are trivial. And in this area, so as I said, the formulation is easy, but to calculate it's hard question. And in this area, we have a big theorem in 1950s. Eilenberg and Ganea proved this following theorem. It's that given a discrete group, LS category of group equals to cohomological dimension of group. And we can call that cohomological dimension of group is also well-known, well-studied in the algebraic community and the topological community. And here's the definition. So it's a just supreme of K such that K's cohomology is not zero, and the M is the Z gamma module. And so in this site, so we want to have it similar. The question now been asked. So what we can say about like the or LS category of group homomorphism? Do we get equality? So in this area, so now before the reformulating or formulating the question, first thing that I looked was cohomological dimension of group homomorphism. Unfortunately, I couldn't find it in the literature, like classical ones. And but luckily, I was able to find it in the mass overflow. The question, basically, Mark Grant from United Kingdom defines the cohomological dimension of group homomorphism is a maximum number case such that there exists Z pi modulo M with non-zero induced homomorphism. And he defines this and asks this question, the following question. Okay, is there epimorphism, in other words, surjective homomorphism such that group cohomological dimension of group homomorphism is strictly less than cohomological dimension of like domain and codomain? We know that it's less than equal, but the question now he's asking is, do we have an example such as we have a strict inequality? And answering to his question, Tom Goodwill from Brown University gave a positive answer. And his example, well, I said it's not easy one because it has to do with extension and purely algebra. And Mark Grant asked, okay, I haven't accepted your answer. What I'm looking is is there epimorphism between geometrically finite groups? So example that Tom Goodwill gave was like his group is infinitely generated. So in this area, now we formulate our question. For any group homomorphism, do we have equality? In other words, LS category of group homomorphism equals to cohomological dimension of group homomorphism. In this area, one of the students of Alexander Danishnikov, Jamie Scott, considered this conjecture for geometrically finite groups. And he proved the result holds for the injective homomorphism, and also like it holds for if we choose gamma and phi to be free groups and the free abelian groups. And well, what is, let's recall geometrical finite group if there is like the finite Eilenberg-MacLane space like CW complex, or we can take simply a short complex. In general, there is a notion that geometrical dimension is the minimal dimension of the various Eilenberg-MacLane spaces. So remark here, like I said, like this example, in fact, this conjecture is false if we do not assume geometrically finite. Well, the reason is like Tom Goodwill's example also can be considered as a counterexample. But if we note that from his example that the gamma is here infinitely generated discrete group. So we are looking for finite ones. Now, before answering or going to the conjecture, we want to first answer the first Mark Grant question. Well, is there the simple example of the epimorphism or surjective homomorphism? Yes, there is. One example would be just take this homomorphism, the free product of free groups with n generators and free abelian groups with n generators mapped to the free abelian n generators. Well, how we define is like the first factor is like we will do abelianization. For the second part, then take a free abelian group n generator, just project to the first coordinate. then from here we can see that cohomological dimension of the group homomorphism is 1, and here like a cohomological dimension is, we are using this theorem, like cohomological dimension of group like equals to geometrical dimension of group, except when n equals 2. So from here, you can think about this pre-abelian n group to be just an n-dimensional torus, and pre-group n generators, it's basically the wedge of the circles. And from there, it's easy to see that the cohomological dimension has to be n in both sides. So, and to answer that we have to do some technical stuff. So let's recall some join in topological spaces. For us, we will think about formal sum, and where TIs are like real numbers, some are like 1, and we omit 0 times xj. And here now, we will consider five-wise joins of fibration. Again, it would be fibration, and you can think about as it's when n equals 2, it's just a pullback. Like you have these two maps from and map to the same point. So for notational, if xi is just x, then we will use this notation for the oops. Okay. So notation wise, we will use this one, and the notation for the fibration is n plus 1. Just tells us how many times we have to iterate, and based on what space. So in this area, now we want to consider a Ganea-Schwartz approach. And we know in algebraic topology, given a map can be turned to the fibration. And so this base point and the map to the space, we can turn this one into the fibration. We'll get at a path space fibration. And this is called n plus 1 iteration of this a path space. We get a Ganea space, and the fibration is called the Ganea fibration. And there's a theorem that says that if the x space is A and R absolute neighborhood to a track, then the LS category of X is less than n if only if we can build a section, or if this fibration has a Ganea fibration has a section. This theorem easily generalized for the map, for map between A and R spaces. Same thing holds. We say that the LS category of map is less than n if only if there exists a lift with respect to this fibration. And to note that this, the Ganea fibration is a functorial. So and now instead of considering all the homomorphism, so we want to just consider epimorphism, and well, then we're going basically given the homomorphism, so we can restrict the codomain to the range, and we get following results. Namely, the LS category will not change, and cohomological dimension of group homomorphism stays the same. Then our main result, the main result, we say that all for homomorphisms between the finitely generated pre-nilpotent groups, then the conjecture holds true. Namely, LS category of group homomorphism equals cohomological dimension of group homomorphism. And now we say in general the conjecture is false even if we consider the geometrical finite groups. The example that we gave was namely for the spaces, closed aspherical four manifold, then onto the torus three-dimensional induces epimorphism on the fundamental group such that LS category of this group homomorphism equals 3, and the cohomological dimension is less than 3. And the remaining for 5 minutes, let me sketch just the proof. So for the first part, like we need the following technical lemma, namely to like if we have like a finitely generated torsion-free nilpotent group, if there is a epimorphism between them, we can realize it as a locally trivial bundle of nil manifolds, and the fiber being a nil manifold. And this lemma might be trivial for the experts, but I couldn't find that in the reference. I could find the one that said like nil manifold can be realized as iterated principal iterated circle bundle over circle by Igor Belgrad. And I know that like torus bundle over nil manifold is a nil manifold again. And so, but for this lemma, so we have to prove for this lemma. And for the second one, it's like, oops. So for the second one is what we are saying that for every local trivial bundle of closed aspherical manifold with dimensions m and n, and what we are requiring is that with a compact connected fiber, then induced homomorphism is non-zero. Here the pi is a fundamental group of this like codomain n manifold. From these two, so we can see that like to prove our theorem, we have to consider just for the epimorphism. And but if we consider epimorphism, but first lemma said that well, it can be just like a local trivial bundle of nil manifold with fiber nil manifold. Well, we know that nil manifold is the compact. So and the second lemma tells us that well then like ends like cohomology is well in proof homomorphism that we get non-zero homomorphism in the ends. Well, then we get since LS category of map is less than equal to minimum of like domain and the range, then we get equality. Okay, next one. So for counterexample, like we have to use a Bolotov close like Bolotov constructed, in other words, for manifold such that it has a cohomological dimension 3, but classifying map cannot be deformed to the second skeleton of classifying space. So we have to use this one because it gives us that like LS category of this like Bolotov manifold is like greater than 3. So it's not less than 2. If it was, then we can deform to the classical for the classifying second skeleton of classifying space. So his manifold is like it's easy to like if we consider just like a pullback diagram. So we have like this is a one map. So and the second one is like you can define it as like it's like cross product, but the second one is identity. H is a hop bundle or hop fiber bundle, and that like now both of example is going to be just a pullback of this like map. Here G is this map is three-dimensional torus collapsed to the point, and that so now we have both of the examples, and so from this example we take this into both of example and prove that it has the properties that we want. In other words, we say, okay, the P map induces the isomorphism between the fundamental groups. It's easy calculation. We use the Van Keven theorem. And for second one, we say that it induced homomorphism is a trivial if you consider any pi modules or Z pi modules. And this guarantees us that the cohomological dimension of group homomorphism is less than 3. And the C and the D, basically, we needed to prove LS category of like group homomorphism equals to 3. And then here, like we needed like this fact, namely every closed manifold, since the both manifold is a closed manifold, there is a hyperbolization, which is the map of degree 1 of closed spherical manifold, which is surjective on fundamental groups. And in addition, we can say that it induces isomorphism between the stable tangent bundles. It might not be isomorphism on tangent bundles, but it will be on the stable tangent bundles. And here, like we give a reference, it's Davis and Yanukovych, and here's the reference. And thank you for listening.
Wonderful. Let's thank our speaker. Thank you so much. Any questions? Again, feel free to unmute yourself or put them in the chat.
I think so. One remark that I want to do is for this theorem. So for here, for the first theorem, to prove the theorem, we just needed these two lemmas. And for the first lemma, and can we extend this lemma for the just polycyclic groups? Like what we needed was like kernel of this homomorphism to be finitely generated, to have like closed manifold or closed fiber, and still the result holds. But to prove this lemma, I heavily rely on the central extension, because for nilpotent group we can do central extension. And yeah, I don't know, it would be a good idea if we can somehow extend it just for strongly polycyclic or polycyclic groups. And thank you.
Are your techniques different from some of the other results that were proved by, I can't remember the name, but for the other groups that are shown to have this equality, did you use completely different techniques, or are they sort of similar?
Oh, well, the proof Jamie gave was like just 3 groups and the 3 abelian groups. And over there, pre-abelian groups, it's basically mapped between the torus. It's a straightforward calculation. So you don't need this lemma to prove it. And but here, so we need it because the tricky part is if you just consider just like Heisenberg group, like the group just circle, principal circle bundle of torus, mapped to the circle, mapped to the torus itself. The Heisenberg group mapped to the free group with 2 generators. And induced homomorphism is the trivial if you consider just regular coefficient or trivial coefficient, but it will not be trivial if we consider twisted coefficient. So we needed like twisted coefficient. We are working on the local coefficient, so we need this lemma. Well, in other words, this lemma guarantees that.
Thank you. Any other last minute questions here for our speaker? Great. Okay, well, thank you again, and we'll be back in